Chapter 5, Section 8, Solving Applications. I kind of look at this first problem and they try to make up real world problems to fit more of our skills that we're trying to practice. So, they always say, what am I going to really use this for? And I'm going like, well, I don't think you're going to run into this problem in the real world, but it's really setting up saying, hey, can you translate this type of problem into algebra? And that's what applications are. If we can take or get practice at translating English, in this case, to algebra, um, we're going to use our algebra to solve this. Well, they go through some strategies again for applications. This shouldn't be new information, but you want to familiarize yourself with the problem, and then this case, and then translate it again. We're going to actually take the words and pull out variables and operations and create an equation with an equal sign, right? And then solve that equation. And in this case, we've had similar problems to this, and usually um, we've had to kind of force a couple things and take different routes. But as we get more skills, actually the translation part should be uh, more straightforward in a sense. So we can write the equation. In prior examples, before we dealt with quadratics, we would just try to avoid the idea of a quadratic and try to create a mathematical or an algebra situation that avoided that. Now we don't need to. So anyhow, this race here they're talking about is that these two racing boats were assigned consecutive numbers. In other words, one right after the other, and then you need to remember what that means. And then they tell us that the product of those two numbers is 156, which you can say, hey, you got two numbers and you're next to each other, and your product, rather than tell you what the numbers are, they would just say the product of them is 156, which would seem kind of funny. But that's the information we have, and so we're going to look at that. And they show a picture here. I don't think you have to draw pictures of sailboats. But I'm going to have one number is going to be x. Then if it is x, if I say the first number is x, the next consecutive one would be x plus 1. So there is a good part of that, and that's what they're talking about. Familiarize yourself with all this stuff. If you're not quite sure what consecutive means, you should look that up. And what they do then is say, well, if I had like 49 and 50, they're consecutive. What would be the product of that too? Then might cue you up and say, well, I'm going to multiply those two numbers, right, to get a product. You can get familiarized that with. And sometimes that is saying, well, let's take the variables out and just play with some numbers, and what would you do? And a lot of that will give you a hand in writing this equation too. So they reword the problem before translating. Rewording the first boat number, well, the translation is x for that, times, which is a translation already, is saying the product, which means that we're going to multiply these two things. The next boat number is going to be this x plus 1. So I end up with this equation, x times quantity x plus 1 equals that product they gave us, which is 156, answer to the multiplication. Well, to solve this kind of quadratic, I need to get it equal to 0, just like we've done in prior sections. So I add a negative 156 to both sides. Now, if I can factor this, hey, I got something I can do with this, because these two things multiplied together make 0 now. And I can say, well, the only way that can happen is x minus 12 in this case has to equal 0, or x plus 13 has to equal 0. So what we end up with is 12 and negative 13. And I see this happen a lot. There's actually two solutions to this quadratic equation, but then we need to go back into the real world. I don't think that they're going to have negative numbers on their boat numbers. They probably are going to be all positive. So they're going to say, well, we should probably throw out that negative solution and then just use 12. So let's check that. If one boat number is 12, The next vote number will be 13. Does 12 times 13 equal 156? Yes, it checks. You don't check it into the equation, you check it back into the original problem and say, does these boat numbers work? So check it back to the original and do that. This next example is about this building cutting boards, and they're talking about relationships of length and width, and there's going to be a couple other things we're going to need to bring up. It's good to go through these examples because you're going to have to know how to get area of a rectangle, I'm assuming here when we look at this, and that's what they're talking about here. So we first make a drawing, and that I'd say, especially when we're talking about rectangles, triangles, we're going to get into Pythagorean's theorem a little bit later in this section for triangles, and draw a picture. So we draw a picture of a rectangle. I don't think I'm going to draw a cutting board with cheese and looks like lemon or something on there, right? And a knife. And there's a steak and asparagus right there, right? I don't think I'm going to draw all that. I'm just going to draw a rectangle. And then we start defining our variable to do this. So if I say the width of this rectangle is x, what would be the length? Well, they tell us that the length is twice as long as the width. And so I put x here, then what would this be? I'd get 2x. What if I put x for the length? Well, for this to be true, I'd have to have half this, or half x here. Either one will work. You may want to play with this a little bit and try to avoid the fractions. We usually have more errors around fractions. So define it in a way, but either way works. I could say x and 1/2 x, or x and 2x. It'll still work out the same way. Then we reword the translation as follows, right? Mostly right from the picture, I'd say the area of the triangle is the multiplication of length times width. So I need to know how to get the area of a triangle. So that's where they get this 2x times x, length times width. They already tell us what the result should be in centimeters squared. I could actually leave that there if I wanted to, but I'm going to end up with 800. So I end up with this equation. 2x squared equals 800. Well, I can't do anything with it equal to a number. I want it equal to 0 to use that principle of zero products, and so I add a negative 800 to both sides. Then I factor. Well, again, look for common factors first. This would be very easy to miss here. You say, hey, I don't have difference of squares because 2 is not something squared. But 2 is a common factor between these two terms. Make sure you factor that out. And I get 2 times the quantity x squared minus 400. Well, x squared minus 400 is difference of squares. So I can recognize that, factor that to be x minus 20 and x plus 20 in my terms of my binomials, right? So I do factoring difference of squares, and I check, is there anything else I can factor? And it's no. Well, then for this product to be equal to 0, or the answer to this multiplication, then these factors have to be equal to 0, or one of the other has to be. So I solve for that. I get 20 and negative 20. So I have 2 solutions to this, is what it's looking like. And then again, I go in here and I say, since width must be positive, we're talking about length, that negative 20 doesn't make any sense, right? And so we're going to take the positive of 20. And then it's also pretty important to remember, what does x mean? The way I drew my picture, right, x is the width right here. So if I find out that x is equal to 20, what is my length? It's going to be 20 times 2, or 40. Does 20 times 40 equal 800? And the answer to that is yes. So I basically have kind of checked when I'm going through this, looking at the picture again, and I can do that. Now, again, like I said, I could have this x be the length and this be 1/2 x. If I did it that way, I'd end up with x being equal to 40, and I'd say, well, what's the width? Well, it's half of that. So I'd get 40 and 20. I'd end up with the same solution. Again, check back into your original. Dimensions of a leaf. Let's look at this. It says each leaf in one particular philodendron species is approximately a triangle. Okay? Looks like an equilateral triangle. Or excuse me, an isosceles triangle. Equilateral, all the sides are the same size. It looks like it's going to be an isosceles triangle pretty close to that, where these two sides here are the same length. So they tell us a typical leaf has an area of 320 inches squared. If the leaf is 12 inches longer than its width, find the length and width of each of the leaf. So we familiarize ours with the area of a triangle formula, which is half base times height, and that equals area of triangle. Now what they're really talking about when they say the length is this spine of this thing, what that length is going to be the height of this, pretty close to the height of this isosceles triangle, right? So if I know this distance across here, this would be the height of my triangle, and so on. So we define that. So we let B be the base width, good letter choice I would say for base, right? And then what do they tell us about the height? It says in here that the height of this is 12 inches longer than its width. So that would be the base distance plus 12 would be the height of my triangle. So then I take these two expressions, put them in the formula for the area of a triangle. So it'd be 1/2 the base length times the length right here, which is B plus 12 equals 320. Now we can show that a lot of different ways and do that, but it's still equal to something that's not 0. So we need to multiply this out. We're going to get this new binomial, or two terms right here, b squared plus 12b. Well, factoring does me no good until it's equal to 0, so add a negative 640 to both sides. Now I have a trinomial, they factor it here, they show the factoring, and I end up with these two solutions here. One is negative, one's 20, negative 32 and 20. Well, the negative doesn't make sense again. So what I found, what does B mean again? It means the base, the distance of the base of that leaf, and then the height would be B plus 12, which is 20 plus 12 is 32. And then we check, is 1/2 20 times 32 equal to 320 inches squared? And it is. So that checks that if we have this conditions for this leaf, this is the actual dimensions of that leaf. Now in medicine they do some things with formulas. This case they're going to give us a formula, and I think based on what we've covered so far, I think you should be able to do that. Really it's familiarizing this thing in here. They're telling us a number of micrograms, and then T is time in minutes. So if they give us minutes or this kind of stuff, or a relationship between these things, and usually what they're going to do is try to say, if I give a certain amount of this medicine, how much time should I worry about before I re-administer something, which is a pretty big deal, especially with some of the types of drugs that are out there, right? So we go through this, we can then substitute 210 in for n, set up that deal. It has to be equal to 0, factor, look for common factors, trinomials, difference of squares, not in this case, but could be possible. And I end up with 2 times that do that. And since we check, there will be in the bloodstream approximately 3 minutes and 7 minutes after injection. Okay, so there's actually 2 things that can come out of these kinds of formula, because it is a quadratic. And a lot of times, you know, that it really takes somebody to understand what they're getting the results of these things, because you're actually getting two different answers for these quadratics.